Okay, let's start slowly. Okay, so I'm about halfway grading the midterm, maybe 60%. Let's talk about a few of the questions and mention typical mistakes and see how to do it properly. Question 1 from the midterm at which you were asked. I'll start my own. Let's see how we're doing. Okay. Question 1 at which you were requested to do exactly what you were requested to do in homework 1, which was to play with a tap where you don't know which direction is hot, which direction is cold, and you are trying to get as quickly as possible to the hot water. And the big mistakes that some people did was not to realize that you don't know t-mean. It was never mentioned what is t-mean, and obviously you don't know it. So people that said, let's put the tap on one direction and then for t-mean and then put the tap for another direction, and that's why you will get a time which would be 2 times t-mean. Well, that's not the correct answer. So they got, I think, about penalty of something like 9 points or 8 points. But the correct answer, people had problems getting to the exact k, and a lot of people got to the value that did everything correctly, but stated that eventually we are getting to k equal 4 because they said the overall time would be t-mean times 1 plus half plus 1 over quarter plus dot dot dot, which is 2, and we are doing it for the both sides, which will give us k equal 4. That is that we can solve the problems in our time equals to 2 times the 2 directions times t-mean, smaller equals than 4 times t-mean. Well, that's unfortunately not correct. Let's change order over here. Yeah. So that unfortunately is not it's not correct, but I took very few points for doing it. Like it's mostly 1 point if everything else made sense. Then the penalty was only 1. Yeah. Sorry, I cannot turn off the sun, so I'm just playing with directions. So yeah, if everything was correct in your answer except that you didn't compute k correctly, then depending on which arguments you made and how did you get to it. I thought that it might be reasonable, so the penalty was between 1 to 3 points. Question 2, I didn't finish grade everybody. I got long list of codes that probably would have run perfectly if I would go to the compiler and try to run them, except that they are exponential. So if I'll try greedily in question 2 to look at hello world, and I decide that I'll start from the end or start from the beginning, doesn't matter, I can start also from the beginning, and then go to the as much to the right as possible, such that on the left I will have one word that belongs to D, and then continue greedily to the next word and to the next word. What's the problem? That you are completely committed to having this part of the parsing of the sentence. That is, you're committed that the breakup will be at the first word in some solution that I saw. So, and some people did not realize that it could be that I should have taken that I have better way to parse the whole sentence if I'll break it, say, after the HE and say that this plus something from the W will become a word, and this plus something of the W will become a word for itself, while hello world maybe I cannot parse if I'll insist on the hello. That is, the hello by itself was a wrong choice, but a prefix of the hello or something that the hello is prefix of would make a much better choice, and then I can parse the whole sentence. So some people did not realize that you cannot commit about the first word, and other people that was aware of it, but instead suggested something that was trying to greedily go forward, parse more and more words, and if you cannot parse the whole sentence, if you got to the end of the, say, nice day, and if you got to the end and you realize that this is, say, not an English word, then you're backtracking your way and try to proceed greedily. And probably in most practical application, it will work just fine. Problems, it can be exponential. So, of course, I prefer the second attempt over the first attempt, because then at least you are aware that you cannot commit for the first word, but you need to be aware that forward and backtrack might cause an exponential term over here, because that you'll now go backward, maybe change the hello to something slightly longer or something slightly shorter, and then solve it differently. So what you're doing instead is the correct answer, which a lot of people did get, was to say, let Ci be the max number of words in the text. If this is S, then in the text S of 1 dot 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 I. That is, I want Ci, that is, the problem with exponential search was caused because you did not use any memorization. You did not remember which sub-words can form together, which substrings are a good starting point. So what works instead would be, let's use memorization, one of the key ideas of dynamic programming, and let ci be the maximum number of words in the string s from 1 until I. And now what do I do? For I goes from 1 dot 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 to n, and I'll of course initialized ci to be, say, minus infinity because I didn't find any words in it, and C0, strings of length 0, will have 0 word of it, so that's the only index that is different. I'm doing the C0 just for because I'll need it in the next loop. And now for I goes from 1 dot 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 to n, and every time that I'm looking at si, say the hello world, I will use j to tell me if j is where I'll suspect is a first character of the word that I'm not parsing. I'm not saying it clearly. I'm at index I over here. I'm at the end of the D. I equals now to the end of the D. So I suspect that there is some word, say world, that ends right here at I. I'll go and look for the beginning of this word. It is for J started N down to 1, down to 0. That is, J is going backward. J is going to look at previous and previous values. And remember, for at this point, I assume that C of, well, by induction, assumption, C of J is computed already and memorized for every J smaller than I. What should I do? I'll check if. I'll set if C of J minus 1, if J is at the end of the last word, I'm asking that can you parse in any way all the words that ends at the O, including maybe previous one, if C of J is larger than 0, and S from J dot dot I is a word in D, then I think that it might be, then at least I have a chance or some parsing of everything up to the I. That is, the last piece from J to I is a word, and everything that came before it is a word as well. And maybe I'll stop here if I just want to see if I can parse everything, and I'll just say Ci to be 0, 1 if I'll ask is parsable or not parsable. Oh, if I'm more careful, I will say if C of S of I to J belongs to D, and let's move over here. And in addition, I cannot see it. And in addition, can you see the end? Not really. If both these, let's rewrite it. if C of j minus 1 is larger than 0, and S from j to I is in D, and in addition, if it is a word, what should be the next value of C I? Remember, Ci, how many words are ending at index I? Then the number of words would be C j minus 1 plus the one word that I just discovered is larger than my current value of Ci, then C of I equals to C j minus 1 plus 1, because I increase Ci at this point. I found more words that can be parsed over here. And actually, I can change it so this condition is actually redundant. Okay, so not too complicated, similar to the clustering of points, definitely much easier than the clustering of points. And yeah. Any questions about this solution? Make sense to everybody? So, okay, let's move on. The C-Fresher, a lot of people got right, but some people didn't know the correct algorithm for the normal Fresher. Most people that understand how the normal Fresher works manage with this problem just fine. And a lot of people got close to the bonus, did not nail it the n square completely because you have memory of how do you initialize the values. So if we start by allocating an array of n square many cells, then in a sense we are already spent n square time just at the beginning. So we need to be careful about how much memory are we allocating, and even if not, then how do I initialize only the cells that I need. But I heard about, I had several of you you're written down for you did great in the bonus, and it is stored in the list of bonus points. Okay, this was not problematic. Many people did it correctly. This one, typical mistakes. I am not asking about two specific lists. I'm asking about a list of lists. So people that describe an algorithm that works only for two lists, that's not great. The option of using dot product made sense to some people, but they also realized that if I'm using dot product with different coefficient, then these two lists, even though they have the same elements because they multiply each element by different constants, these two lists will not be hashed to the same place, which is already a realization that makes you one step closer to the direction, so to the solution. So you need to canonize them somehow. Canonize was like rotating the tic-tac-toe problem, or looking at a string and express this string only using small letters in just storing alphabetic strings, was in question 2. Here, the trick was, of course, to sort the lists before we are comparing them and once you sort them, then then these two lists will be hashed, of course, to the same place because they'll appear identical. Solutions that just sum up the numbers and use this as your hash key. It's not very bad, but in general, summing up elements, as I preached already for the identical files, just summing up numbers is not a fantastic hash function. It could be too often that you have not the same value for all the keys, but only small spectrum of values for all the keys. But it's not too bad. Yeah, and this one I did not grade yet. Yeah. Okay. Questions? Jake, you wanted to ask? Okay. Let's go back to linear programming. So, linear programming, we have in linear programming, we talked about the problem of in linear programming, we talked about the diet problem. It was 2 weeks and many midterms probably for everybody, so I'll refresh your memory about what is the whole diet problems talking about. So we are given the cost of a banana. We are given the cost of a banana. What happens if I decrease my screen in this way? Can I fit both of them over here? In the linear programming, we have the, it wouldn't work. In the diet problem, we have the cost of the banana, and we'll use the x coordinate to represent it because we like geometry and we want to represent everything as geometric problems. And so we will have the cost x as a cost of a banana. We will have y as, restart. We want to find how many bananas to eat per day and how many oranges to eat per day in a way that will provide a healthy diet. Namely, we will get all the vitamins that we need, and hopefully in addition, we will have the cheapest diet that we can accomplish while being healthy. So what inputs do I need for the problem? I need the inputs that will tell me how much a banana costs and how much an orange costs, and how many units of vitamin A do I have in a banana, how many units of vitamin A I have in an orange, how many units of vitamin B I have in an orange and a banana, and so on for a lot of vitamins. So all these are the inputs, and what I'm trying to find are the values x and y, that is a point on the plane, for which all the constraints are satisfied. Each vitamins is satisfied. If I think about the point xy as my daily diet, in addition, I'll try to be directed by the cost function to get the best diet. So to be precise, here is the formal definition, and I'm sorry, the linear programming, I'm very proud that I'm teaching you linear programming because it's ridiculously important technique. At the same time, there are a lot of indices and sub-indices, and today we will also have dot product and vectors. So there is some cost to get used to these notations that might be less pleasant. Okay, types of food, right here I have just X and Y, so my problem is a two-dimensional linear programming. I have only two variables, two unknowns. I have n types of vitamins, J between 1 and n. X is going to be the number of oranges that I recommend daily. Y is going to be the number of bananas, both. And having a square root 2 number of bananas per day is absolutely fine with me. I don't care if it's integer or not. AIJ given to me is the amount of vitamin I in unit food J. That is, if I have only two types of food, then I have A11 that says units of vitamin 1 in an orange. A12 says units of vitamin A, first one, but in a banana. BI is the minimum daily required for units of vitamin J. BJ is the amount of unit of vitamin J, or else it's not healthy enough. And vitamin 1 will give me the constraint that A11 times X, that's how many units of vitamin A you're getting from an orange. A12 times Y, A12 is how many units of vitamin A we are having in a single banana, and Y is the number of bananas that we are going to consume per day. So the sum of these two values is how many units of vitamin A from both bananas and oranges we are getting daily, and this should be larger or equal than B1. And similarly for each other vitamins, and I want to look at it and in the same time find the cheapest diet. So we saw that we dedicated a class and a half to look at this fantastic app that allows me to look at, say, constraints 1, at this constraint, that is what? It tells me that in vitamin, in a banana, I have 7 units of vitamin A, and in an orange, I have only 1 unit of vitamin A, and it needs to be larger or equal than 65. So if I just look at this constraint by itself, if I just look at this constraint by itself and ignored everything else, then you see that there is this line. Here are points which are XY such that you are just getting 65 units of vitamin A per day exactly, and moving anywhere to the right side of this line, you're getting at least, actually more than 65 units of vitamin A. Similarly, changing our attention to vitamin B in an orange is 4 units, in a banana there are 2 units, and you need at least 70 units of vitamin B per day. So every point XY in this direction is giving you even more than 70. And if you're on the line that is bounding this region, this half plane, then you're getting, on the line, you're getting exactly 70 units. Now, if you want to satisfy the requirement to find XY that satisfies the requirement of both vitamin A and vitamin B, you need to take the region from vitamin A, you need to take the region of vitamin B, and every diet that is in both regions, this is at least that corresponds to diets that you are getting both vitamin A satisfied and vitamin B satisfied. Adding vitamin C to the picture, let's turn off these two guys. Adding vitamin C to the picture, here is another region, and now I need to be in the intersection of all three regions. Let's add yet another one, intersection of four regions. Units in vitamin A, unit of vitamin B. So the region that we actually need is an intersection of all these regions. This polygon must be a polygon. It even must be a convex polygon, where every point in this polygon corresponds to a diet that satisfies both these constraints. A region that eventually looks like one half plane, another half plane, another half plane, another half plane. Half plane is a region that is in the plane but bounded by a line, and you consider all the intersection of the region over here, and this is a feasible region. That is, the diet we are after must be somewhere inside this region. Okay, let's wait a bit with the C constants, because with the cost constant, we'll get back to it a bit later, but before that I want to teach you a bit of vector notations, because I think that it will be easier to understand what's happening in the cost after we'll see about the vector constants. Everything is good so far, at least definition of the problems. Everybody, okay, great. So let's keep this slide. Actually, I want to get to it later. And where did I lose this slide? Okay, let's talk a bit about dot product. So again, it's a bit of a learning curve, but I think that all in all it was effort, both for what we are doing today, as well as your future in whatever is waiting for you in the future. I think that I cannot find a better algorithm to give you, to prepare you for algorithms that you need to know, that there is a chance that you'll actually use these algorithms later. So I'll take here this wonderful empty grid, and I want to speak about vectors. So vector in my setting will be has a few different, has a severe case of multiple personalities. We can think about a vector as many different things. To start with, I'll think about a vector. Go away. I'll think about a vector as a d-dimensional list of numbers. Vector in the d-dimensional world is a list of d numbers. I'll give them names. The first number is v1, the second number is v2, v3, all the way up to the vd, namely the number of the last number of the vector. In 2 dimensions, it will be just v1 and v2, or just x and y. Okay, so and to tell you that this letter represents a vector, this list of numbers, rather than just a single number, I'll put I'll put, at least if there is any doubt, I'll put the arrow right here on the top. Sometimes you'll see it with an arrow, sometimes you'll see it with just a bar, but sometimes you'll see it as boldface, but we are using slightly different letters to denote that it is a vector. So one way to think about the vector is as a list of D numbers. Another way to think about this vector is in the plane. I can think about the point V1 and V2. It is a point, and I'll think about the vector as just a point. And sometimes you will find it useful. So every vector is a point, but every point is a vector. And this is true and false at the same time. Some people will argue with me fiercely at this point. Sometimes I'll think about this vector as an arrow that starts at 0, 0 and ends at V1, V2. So sometimes it's just a point, vector AB. Sometimes it's the end point of the arrow. Sometimes we'll think about it as the whole arrow itself, from 0, 0 all the way up to 1, 1. And similarly, every point is a vector. Every point is every vector is a point. Yes and no. It's a bit confusing. There is a bit confusion here, but everybody that taught linear algebra went through this confusion, or anybody that uses vectors in physics. Say. Now, if I have two vectors, one vector V with arrow at the top, consists of the numbers V1, V2, dot, dot, VD. The other one is U1, dot, 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 UD, because they are all in D dimension. I'll tell you what is a dot product, U dot product V, just a dot between them. And it's written U dot product V is a number, but we call the scalar. Scalar is every variable that is not a vector, just a single number. It is a scalar, and how do I compute it? It will be, take the first number from V1, take the first number from U1, multiply them, put it over here. Now take the second one and the second one, both scalars, multiply them and add them to the first product that I had. Go to the third, go to the fourth, go to the fifth, until you're getting to VD and UD, multiply them, these are the last one. Now sum up all these products. This is what U times V consists of. Quick example. If V equals 3, 5, 2 and U vector equals 1, 3, 7, then U dot product V is, take the first times the first, that is 3 times 1 plus 5 times 3 plus 5 times 3 plus 2 times 7. You see everything here? Plus 2 times 7, which is in turn equals to 3 plus 15 plus 14, and once you'll be able to pull your calculator and compute it. That's what U times V implies. And now it has lots of geometric meanings as well. Namely, if I have two vectors, these were vectors, of course, in 3 dimensions. There are 3 numbers over here, X, Y, and Z. If I have two vectors, two non-zero vectors, Yeah, I can think about them as arrow emerging from the origin, and here is u vector, here is v vector, and I'm asking what is u cross product v, then u cross product v is 0 if and only if u is orthogonal to v. If and only if the product is 0, if and only if the angle between them right here is 90 degrees. Okay, so it has a very simple geometric meanings of the dot product. We don't need to prove it for this course, but it's definitely worth knowing. And what we definitely distinguish is a vector is a list of numbers, a scalar is just a number, I said it already. If you want, you can think about a scalar as a vector in dimension 1, but I have no idea why you'd like to do it, but you can. Let V be a vector, and we can think about it as an arrow, I said it, emerging from 0, 0 to the point V, point that you will get by dropping these values. And now I want to ask about all the other points, P or vector P, let's say P equals AB, such that P dot product V is fixed, P are all the A and B. What is P dot product V? I'm just writing it explicitly. It's the first parameter of P, namely A, times the first parameters of V, namely the scalar V1, plus, that's just repeating the definition of dot product, B times typo V2 should be equals 1. Okay, so where are all the points P such that P dot product V equals 0? Well, quite easy. We're going back to we need to go back to our whiteboard. We will look at the vector V, and we will ask, here is a vector V, this point over here, and I will ask, is a point 0, 0, if P happens to be 0, 0, then it is true that when P equals the vector 0, 0, it is true that P dot product V equals 0. Yes, it's true, because the point 0, 0 times dot product with anything will still yield 0. So this point is over right here. There are other points, and as we said, if I'm just going in any direction that is orthogonal to P, take any vector over here, any point P such that P is orthogonal to V, put it as a vector, is every point of it will satisfy P dot product V is equal 1. And if you want to play with it, go to GeoGebra, which is, I find, as a fantastic tool to get intuition to things, and write in GeoGebra, V equals, say, to 2, 3, and you'll see V appears as a vector. By the way, GeoGebra will give it a small letter to denote that it is a vector. Capital letters are points, small letters are vectors. That is, if and I'll want to ask what is all the x and y, all the points x and y in the plane, such that xy dot product v equals 0, and you see the line that appears right here. Okay. Now, you might ask, what happens if I'll take all the points v such that v times xy dot product v equals same xy, same v, but instead of 0, I'll write 1, and what appeared is another line that is quite close, that is parallel to the original line, but is a bit away from it. It moved by some amount to, where did it move to? It moved exactly, if you look at the vector v, the blue line moved a bit in the direction of v. If I'll write instead of 1, if I'll replace it by 2 or replace it by 3, I will get values for which p times v is larger and larger. If I'll take, that is a line moving parallel to itself and all the time orthogonal to v. If I'll replace the 3 by the minus 3, then I'm moving to the opposite direction, moving to values smaller than v, smaller than 0, 0. And in general, let's repeat the same exercise. First, let's see it in the slide. So if I have p and v, if I have p and v, here is v, 0, 0, ab, whatever values ab, the line L, and let's use this notation from now on. I can write a line, when I'm referring to a line, I can think about the line L as all the points, small, curly L. L has all the points P such that P dot product V equals 0, or some equation is satisfied, and as we know that it's a line, and I'll sometimes abbreviate it by just writing the line L defined by all the points P, or the points X, or the vector X, such that P dot product V equals 0. And what is this line? It's always orthogonal to the vector V itself. And in general, if you have some other point, Q over here, oh, I have something in the animation, the line, the line P dot product V equals 1 is parallel to this line, just a bit shifted. The line P dot product V equals 2, shifted. And if you have a point Q, some point in the plane, and you want to find all the point P such that P dot product V, all the point, and you want to find the line that is parallel, orthogonal to V, a line orthogonal to the vector V. However, this line is actually going through Q. Then you can just write all the points P such that P dot product V equals P dot product Q. Q is a point that you started with. You want the line to go over it, and that indeed will be satisfied. Okay, so back to our beloved GeoGebra. I'll generate a point A, and I'll ask for the same vector V that I had before. Where are all the X and Y? In GeoGebra, I need to use these letters, X and Y, such that XY times V equals X, equals A times V, and it's a line parallel to itself, thank God, and going through A itself. And the proof of it is very simple, because obviously if the point Q is on this line, and I want, and this is a line orthogonal to it, then you first need to check that, well, v times q equals v times q. This is usually correct, that v times q equals v times q. That you have the point, v times q equals v times q. This is correct in some very naive way. And if I have another point q prime on the same line, then what is the direction of the vector that goes from q? You don't need to know this proof, but if you're familiar, if you know what are vectors, it's not a problem. Look at q minus q prime. What is this? It's a vector. Where does it going from? It's a vector that goes from q to q prime, both points on the line, and you want that q minus q prime, this brown vector, to be orthogonal to v. I just said I want the line to be defined by all the points which are orthogonal. Q minus q prime visible, yes, the part without the blurring q minus q prime should be orthogonal to v, that is, therefore dot product should be equal 0, which just implies that qv minus q prime v equals 0, and move the q prime v to the other side of the equation sign, and you'll get exactly what we wanted. Any questions? Now, when you know what is this vector, I can ask you, you know what is this vector calculation. I can ask you where are all the xy. GeoGebra, please don't let me down. Qy times v, all the points xy, such that equals 0. Well, we just saw that's a green line that appeared right here. This is a green line. Where are all the points xy times v is smaller than 0 instead of equals to 0? Of course, everything below the line just got highlighted. These are all the points for which xy times v is smaller than 0. And if I replace it by large, surprise, surprise, it will just be the other side of this line. Let's get back to our slides. So let's redefine using all these new notations, all the new toolbooks that we have. Let's now try to define the same linear programming problems that we had before, namely the diet problem. I have j types of vitamins, I have n types of vitamins, we might everybody. X will be the number of oranges that we recommend daily, y is the number of bananas recommended daily. I'll create this every diet, I can assign a vector to it. This vector, I'm now recycling x, but that's where you'll see in every library that defines it. The vector x consists of the small x without vector, that is a scalar, the x value, and the y value of a point. Sorry, but that's how it goes everywhere. The vector x is not this x over here. The vector x has as its first coordinate the x value and the y coordinate as its y. And if I had z and w in 4 dimensions, then I would do it. In our case, it's just every point x is representing a diet. Aij, we said, is the amount of vitamin I that we need in the diet. Aij is how many units of vitamin I do I have in types of food J. that is either j equal 1 or j equal 2. So in this case, I can write aij. People, is this large enough? Can you still read it? Yes, no? Somebody? My text goes somewhere. My Zoom goes somewhere. Okay, thanks. So now if I write the vector AI, what is a vector AI? Its first coordinates, I can write whatever I want, so I'll define the vector AI as AI1 and AI2, these two constants that I'm getting from food administration, I don't know. Somebody that knows anything about food will give me these vectors AI. In this case, I have only two types of food, but very soon we'll work on 3, 4, or D types of food, which will make it a D-dimensional problem, which now means that if BI is the minimal daily required of the food of BJ, so is the food of vitamin J to be a healthy diet, what is its constraints in food I? AI vector times X larger or equal than the other scalar BI. So I need the food administration to tell me what is the AI and what are the BIs, and I want to find a vector X that will satisfy this inequality. And as we've seen multiple times, this is the half plane. Right? This was a half plane that we saw right here. XY times XY times XY times, if the vector AI is 2, 3, larger or equal than 0, you need to get some value of vitamin 1. At least anything above 0. Change it to be 5, and that tells you that here are all the points for which you are getting from both banana and oranges at least 5 units. Okay, I understand. So OBS is using the, yeah, it's interesting. Define what is the boundary of the region. Okay, now we are talking about the cost function, and in all the linear programming problems, the cost function needs to be linear as well. You told me C1 and C2, which is the cost of a banana and the cost of orange. C1, cost of banana, C2, cost of orange. The vector C, which is the pair of the two vectors. And we want to minimize how much money we are spending on bananas, how much money we are spending on orange per day. Written as using vector notation, it will be, the cost function will be C, consists of C1 and C2, fixed, times X. X is a variable vector. What is small x and small y should be as small as possible. Going back to our app, that's the point where I'll get rid of these annoying guys, and I let all of you change the cost of and look changing the budget that you might spend, and so you can when you say the cost of the banana is 0.4 dollars per $0.4 per banana. Cost of orange is 0.5. Where all the points all the diets that will cost me exactly $68.9. These are all the points along this line. Each and every point along this line gives cost exactly the same, and that's what I can get with $68.9 per day. Had I changed the cost of orange, change the cost of day, then this line will be different. But still, every 2 points on this line cost exactly the same. In addition, we required a healthy diet, namely all the vitamins define the feasible region, this purple region over here, only healthy diets. And if I'm trying to minimize my budget, so the diet that I'll take is anything along this line. If I insist on spending at least 68.9 or exactly 68.9, I need to be on this line and inside the purple region, so I'll get healthy diets. That is, this point over here will not be a healthy diet because it violates, I think, the first vitamin. Hoping to spend less than 68.9, I'll start to decrease my budget. Now my daily diets all cost only 34.1, so I'm looking at much cheaper diets. And if I'll keep decreasing the budget, I'll finally hit this vertex over here. That is a last point. That this line where it moves parallel to itself will be the minimum. Looking at the vector C, that's the vector C, C1 and C2. It is orthogonal to the line. Believe it, let's make my banana cost a bit larger so you'll see that C actually changes. And if I'll move in the direction of C, then the diet will be more and more expensive. To be precise, this is the direction at which I'll get the maximum increase. So that would be maximizing the, say, revenue that you are trying to make from selling bananas and oranges. Since we are the consumer and we are trying to minimize it, we want to move exactly in the direction opposite to this vector, minus of this vector, putting just the opposite way. Again, moving in V will increase the cost, and trying to move as fast as possible to get a cheaper diet, I'll move just in the opposite direction of what C points to. That's a new point, clear to everybody. It was not there last time we talked about a diet problem. Okay, moving along. In general now, in every linear programming problem, we have a cost function, which is linear. We have constraints, which must be linear as well. Linear means no sinus x, no x squared, no x times y. These are all quadratic terms, and we need them all to be linear. And linearity is actually less important for us. Being convex is really, really important. We'll talk about it more. The solution to the linear programming problem, anyone, is a point in the feasible region, what you are obtaining as all the vitamins, and is always the extreme point. Somebody point to me in some direction and told me the wind pushes you in this direction. So the solution will always be a convex polygon, and if it has any solution, then there is a solution which is also a vertex of the polygon, right? It's the last point that I hit inside this region. I'm not sure that it always is this point. This is the extreme point, the cheapest one, if my diet was, if the costs are what's written right here. If the cost of a banana will be much cheaper, then I'll get to the cost that appears the best, my best diet will be right here. And similarly with different ratios of cost, I can get any vertex actually to be the feasible region. Here is the direction of the wind, and it will push me in this direction. And we talked about convexity in the last class that we discussed linear programming. Just to tell you very quickly, convexity means a shape is convex if every 2 points, P and Q, the whole segment connecting them is also inside the shape. You have my shape. If you have 2 points inside the shape, then the whole segment connecting them is also inside the shape. And this little theorem that says if you are pushed in this direction and you are inside a convex polygon, how do I know that it's convex polygon? Because each vitamin by itself defines a half plane, which is convex by itself. And if I have two shapes that are convex, then their intersection, every point that satisfies both vitamins in intersection, is also convex. So the feasible region is always convex. And if I'm pushed by the wind, and the wind tells me, keep on in this direction as long as you can, you'll always end up at a vertex. So you can always end up at a vertex. Possibly this vertex is not unique, but there is always a vertex that satisfies, that gives you the optimum. Right? This one is for this direction of wind. What else can happen with a feasible region? It can be empty, or it can be unbounded. Solution might be the intersections of these three half planes. They need to be on the right side of this line, above this line, but also below this line. And it's easy to see that there is no point in the intersection of all the three. The white points that you see here are points that is in none of them. And these points are only on the brownish half plane, but not in the other two. So it's possible that there is nothing in the feasible region. It's possible that the solution is unbounded, or it's possible that the solution is not unique. If you're trying to go down, if your cost function is only to minimize the height, then every point on this bottom edge will give you exactly the same revenue. But it's enough to check only the vertices of this convex polygon, because one of them will give you the optimum value. Right? If you start going downward, you hit an edge, and now you can go left or go right, it doesn't matter. The cost function will not increase until you hit a vertex. And it's true in 2 dimensions, it's true also in 3 dimensions, where you might fall down inside a box. Let's take my Advil box. You fall down inside the Advil box, go down until you'll hit the bottom part, and you'll move down until you'll move on the bottom floor of the box until you'll hit an edge, and then you can continue along this edge until you'll hit a vertex. However, it's a real blessing that we don't need to check each and every point in the feasible region to ask, are you the optimum diet? It's enough to only check the points which are vertices of the feasible region. So the simplex algorithm, which is by far the ultimate answer to every question, fantastic algorithm, runs very fast, even for enormous inputs with tens of thousands of constraints and tens of thousands of variables. This algorithm will say, I'll think about the feasible region. I'll catch a vertex in the feasible region, and then somebody told me about the steepest descent. I will try to walk along the boundary of the feasible region, but I'll walk along the boundary until I'll hit another vertex. And maybe I'm in the global optimum in this other vertex. I'm working only because I'm looking at the cost function and I see that it's pointing downward. So the vertex that I started from, the vertex that I, sorry, the vertex that I started from, this one was not the optimum, which I can find because I can locally look around it, and I see that it's actually quite bad. Any direction that I'll move towards the feasible region will improve it. So I'll pick an edge that will improve it and walk along this edge until I'll hit another vitamin constraint. Another constraint. I cannot keep on going along this edge. However, as I moved along this edge, I improved my cost. I paid less or paid more. I improved my cost, but I cannot continue any further. That's why I'll pick now a new direction, walking along a different edge until I'll hit to this vertex. And from this one, I cannot locally improve it. And because of convexity, this is the only optimum vertex. I don't worry about local optima versus global optima. I'm not worried that this, if I'm trying to look at the lowest point, but above this region, if I'm hitting this point, it is a local minimum. It's very low. I cannot locally move and improve it. However, it is not the global optimum, which is right here. The convexity at the linear programming buys you that the local optimum, you cannot slightly move and improve it, is also the global optimum. That's fantastic. So we have the simplex algorithm, and so the simplex algorithm is the cost function without loss of generality, WLOG points downward. I will start from some vertex. It's pretty hard to, you can imagine it in 3D, and a textbook that I read about linear programming actually said that if you are successful in imagine how it looks in 4 or 5 or 6 dimensions, so if you can imagine it, you need to go to talk to somebody. But 3 dimensions, you can still imagine what happens in 3 dimensions. That's just the intersection of half spaces instead of half plane. Let's take this little box. It has faces on its side, but my camera is so slim that you cannot see it right now. So, and the simplex just improves from one vertex to the next to the next. So remember for future exams, every time that I ask you how do you handle large linear programming with lots of variables, a lot of constraints, you'll say we are using the simplex. And using the simplex is actually very easy for you because as students, you can use a library called Cplex. The similarity of the name is not accidental. Cplex. This is a library that IBM owns, but gives student and faculty free version to play with some limitations. So there is also libraries that are open source. But that's pretty much a big library with a lot of time and money invested in making it optimal. So a very natural question is a simplex move from one vertex in the feasible region to the next vertex? Feasible region, just to remind you, points that satisfies all the constraints. Is a simplex starts from one vertex, it moves to another vertex, it moves to another one, but does it start by computing all the vertices of the feasible region and check each one individually? Not really. The reason that it works so fast is that it avoids looking at most of the vertices, the huge majority of the vertices, because if we are living in R dimension and we have n types of vitamins, let's say we have 4 types of foods, but n many vitamins, then the number of vertices in the feasible region is actually n to the d half. It's exponential in the dimension. It's a curse of dimensionality. Everything becoming worse and worse as the dimension goes up. Adding more vitamins, more constraints is not particularly expensive. The algorithm actually is not going to notice it, and we are going to cover a linear time algorithm to handle everything in 2 or 3 or 4 dimensions. But in higher dimensions, we are getting things that are exponential. Now, this is a worst case analysis, and the simplex is a great example that there is a difference between being pessimist and looking at the worst case versus what actually happens in reality, because in reality, it's extremely hard to construct inputs that the simplex is slow. It's extremely hard, and it means that any noise that you'll add to the input perturb it a bit, and already the number of vertices will be under control, and the simplex actually doesn't check all the vertices. It will start from one vertex, move to another one, move to another one, and so on, all the way until you're getting all the way to the bottom, but it avoids checking most of them. What we are going to cover in the next class is, after we'll talk about linear programming in higher dimensions, which I want to do because here the vector notations will become very useful. And then I'm going to start with an algorithm that runs in 2 dimensions only, 2 types of foods. It will run in n log n time, or the version that I'll show you will run in n cube time, and just construct all the vertices and in n to the cube time, and then we'll see how to improve it to linear time, and that's going to be quite surprising and one of the brilliant algorithms that I know that makes really, I wish it was mine, but it's still very brilliant, and it showed a big breakthrough in theory when people started to use randomization to make the algorithm runs fast. So it's going to be quite surprising, I think. It's pretty exciting topics, I think. Okay. Thanks, everybody. Any other questions about the midterm or anything else? Next week, you'll get homework 5. We need to cover a bit more linear programming for it. Okay. Yeah. Bye. Thanks.